Okay, we need to do two things in order to determine the size of an object in a microscope. Number one, we need to measure the size of the field of view. And number two, we need to estimate how many of our specimens fit across that field of view. All right? So there's two parts to determining how big something is when you look into a microscope. Now, again, if you've printed off the notes, you're just filling in the blanks here. If you're not printed off the notes, you're writing like a maniac, which is fine. When you look into the microscope, you see a, what do I want there, you think? What does the field of view look like? A circle. You see a circle. This area is called the field of view. Field of view. We have a field of view, all right? When we're just using our eyes without any lenses or any, any type of optical devices, we have a field of view. It's usually about 180 degrees. It actually is a little more. You can actually see a little bit further back as your eyes, so you can actually see a little more than 180 degrees. If you want to determine your field of view, you simply stand there, you put your hands out in the end, you wiggle your fingers, and if you can see them, as soon as you bring them in, there, I can see them there, that angular distance would be that field of view. It would be pretty close to 180 degrees. So we have a pretty wide field of view. We even have a field of view that goes up, right? We can't see directly up, but we can see out in front of us a little bit. Same with down below. Your peripheral vision allows you to see a little bit, right? That's a field of view. Yeah, you guys all look hilarious. That's good stuff. If you use binoculars, again, you see a circle, like a field of view. And that's just what you can see as you look out. So in this case, the field of view is a circle. Now, let's think about what happens to the size of that field of view as we move to greater magnification. So you guys looked at the E yesterday. You saw the E, and then you went to a higher magnification. When you change to a higher, and this is what I want, magnification, you see more blank, but less blank. Yep. More detail. Excellent. You can see more detail. Which is good. That's what we want. We want to see the detail. But you lose this. What do we see less of? Yep. Area. We see less area. Because we've zoomed in to a particular location. So you see more detail, but less area. Excellent. So it works like this. Blank magnification means blank area. What would you like to put in there? We want the relationship between it. More magnification? I don't like the term more magnification. Higher magnification, I like that. Higher magnification means less area. Less area. All right? The greater the magnification, the smaller the area we're dealing with. And I've got just some images of this. Now, this isn't a classic field of view because it's a rectangle, but it does get it across. A classic field of view would have been a circle, but you can see there, this is an American penny, and as we change to greater magnification, the area is much smaller, but we can see the detail much greater. All right? Any questions on that? It's pretty straightforward stuff. I'm just pointing out probably the obvious that maybe you have already observed. Okay. To determine the size of an object in a microscope, we need two things. We need, number one, a calculation of the diameter of the field of view. How big is that field of view? And number two, we need to estimate how many of our little specimens would fit across the field of view. Because then we can do a simple division, right? If 3 specimens would fit across the field of view, all we have to do is take that diameter and divide it by 3, and we have how big that object is approximately. This is an approximation. This is not an absolute measurement. It's not a guess, but it's an approximation in that we're not measuring directly. All right? So the first thing I want to deal with is how do we determine the diameter of the field of view? And you're going to have to do this procedure in your microscope with a ruler. And during the procedure, whenever you use the ruler to maybe measure a field of view, I want you to snap a picture of it. Even though we're going to be looking at the hair, again, I'm going to ask you to snap some pictures of the hair. I want you to take pictures of as you're measuring the field of view as well. So here is the equation that relates the diameter to the magnification. We just wrote down a moment ago that if the magnification is high, the area is low, all right? Now the area is related to the diameter. The larger the diameter, the larger the area. So another way of saying that relationship is, if the magnification is high, the diameter of that circle is low, all right? Now, when you have a situation where one thing is big and the other thing is small, we call that an inverse relationship. Have you dealt with inverse relationships in math before? Yes, no? No? No, you haven't? Don't worry about it. It means that one thing does the opposite than the other. As the magnification number gets big, the diameter number gets small. We can represent an inverse relationship by putting a ratio of the diameter under high power divided by the diameter under low power is equal to, notice now that the L is on the top, the magnification under low power over the magnification under high power. The H's and the L's are in opposite positions. That's an inverse relationship, okay? All right? Now, we've used low in our note the other day to describe low magnification. What these H's and L's really stand for is the higher magnification and the lower magnification. So if I was comparing low to medium, right, then the medium would be the higher one, and it would go into the high spot on my equation. Does that make sense? Because this equation deals with jumping from either low to high, low to medium, and then medium to high, or maybe low to high. So in this equation, the H doesn't necessarily stand for high, it stands for higher. The magnification that is higher, or the highest, okay? So I can do calculations from low to medium, and the medium numbers would go in as the higher numbers. I could even do a calculation from medium to high, and in that case, the medium number would be the lower number, and the high number would be the higher number, okay? So we just use L and H to represent lower and higher. Yes? You could. Then high would be high and low would be low, right? That'd be the easiest one, okay? So you could do that. Yep. Okay. This is a rearrangement of this equation, and I noticed some people didn't like the rearranging of the equations. So you could start with this equation and then just, if you wanted to find the diameter under the high, you would multiply by this number and multiply by this number and da-da-da-da, and you would do all your things. We'll do some practice problems in a moment. Okay. So example 1. Now you're not going to be able to draw the picture here. So you might have to make reference to the PowerPoint. But this is how we determine the diameter of a microscope's field. We're going to use a regular millimeter ruler, and we're going to look at it under low power. And you can see there we can measure or see about 5 or 6 millimeters. I'm going to count it in a moment. But by the time we get to high, we can't even see 1 millimeter. We can't even see the entire millimeter mark. So we can't actually use a ruler to measure the field under high. So what we do is we measure the field under low, and then we use our equation to figure out what the field is under medium and high. So low shows us many millimeter markings, which we can easily count, and then we use the equation to calculate the diameter under medium and high, because this might be 2, but it might not. It might be only 1 0.8 or something like that, but we can count this easier. Yes? It should be, but not necessarily. If it were the same brand, I'd say yes. But if it wasn't, it could depend on that objective lens and that eyepiece lens. If their specifications were slightly different, then it may be different. So you might find when you do the calculation for the lab that you get similar numbers, but if you get one that's slightly off, you might find you have a different microscope. Okay? All right. So in this case, we're saying 4.5 millimeters. 1, 2, 3, 4, and a little bit, and a little bit. So we have to make an estimation. We say it's about 4.5 millimeters in that field of view. Now, when we get to higher fields, a millimeter is a unit that's too big. So we like to convert them to micrometers. This U actually should be a symbol that has a little tail on the front that looks more like a micro sign. That's micrometers. There are 1,000 micrometers in a millimeter. So if there's 1,000 micrometers in a millimeter, how many micrometers is in 4.5 millimeters? Shane? 4,500. All right? So 4.5 millimeters is 4,500 micrometers. That might not be the case for your microscope, but that's the case for this example. Okay? The magnification under low is 40. The magnification under high is 400. Determine the diameter of the field of view under high. I'm going to start with the original equation. DH over DL. Well, you tell me what it will be on the other side, keeping in mind it's an inverse relationship. This is so we don't have to memorize it. If you remember that it's inverse, you should be able to figure out what the other side of this equation is. Yep. ML over MH, because it's inverse. All right? Let's fill in the information. DH is what I'm looking for. What's the diameter under low? Shane? 4.5 millimeters. We're going to work in micrometers, so 4,500 micrometers. Magnification of low. Megan? 40? I'm going to put 40 times to represent that it's a magnification. Magnification of high. Megan? 400. X. Thank you. I need to get rid of this on the bottom, so I'm going to multiply both sides by 4,500 times 4,500 micrometers. Here again, times 4,500 micrometers. That cancels those out. So DH is 40 divided by 400 times 4,500. DH equals. We should be able to almost do this in our heads. I could cancel out the 40, and what would I be left underneath if I cancel out the 40 underneath? What are you left with when you divide that off? How's it going? Good. People have moved into your space. That's, I don't know, it's chaos. It's absolute chaos. Anyway, don't worry about that estimation. What do we get here? Somebody calculate it for me. And then share it with me. Megan? 450. 450 micrometers. And that is correct. Notice, the magnification was 10 times stronger. That means the field of view is 10 times smaller, because it's inverse. 450 is 10 times smaller than 4,500. Okay? We're okay with that calculation? Pretty straightforward maneuver? All right. So that's how we can calculate different fields of view. I could do a calculation for 40 to 100. It would tell me the field of view of the 100 times magnification. Okay. Let's do another example here. Yep. Yep. If anybody else needs a calculator, they're sitting out there. If you've got the sheet, you can go ahead and try to calculate that out. You bet. We're doing the same thing. How many micrometers is our low power field of view? If we had 3 millimeters across there, yep, 3,000. When we get down to here, again, dH over dL, it's inverse ml over mh. Notice we're given a medium power, but there will always be a higher one and a lower one. We want to find the diameter of the field of view under medium power. So that's going to go in as my h's. dH, low power, 3,000 micrometers. ml, lower power magnification, 40 times. mh, the higher power magnification, 100 times. Just like the last time, I'm going to multiply both sides by 3,000. dH is equal to. Megan, what do you got? 1,200? 1,200 micrometers. Okay? So calculating the field of view is not so bad. It's an inverse relationship. We just have to keep in mind that there's a higher one and a lower one, and we just have to substitute our information in. Any questions or concerns on that? Pretty straightforward. Okay, so now we know how big the field of view is. When we get something into that field of view, like a hair, or perhaps a cell, or a letter E, I guess, how do we determine how big it is? Well, we just estimate. Really, it's this simple. We estimate how many of those would sit across the field of view. Would it be 3? Would it be 5? Sometimes if we have a bunch of cells, we could actually count the cells across the field of view. We wouldn't have to estimate. We could literally count them. And then all we have to do is divide the diameter by the number of things that go across. Just a simple division. So, estimation. First, we estimate the number of objects that fit across the field of view. Like I said, sometimes if it's a whole string of cells, you can actually count them up. If it's a single object, like a piece of hair, which we're going to do today, you got to kind of estimate and say, okay, I think 3.5 hair widths would fit. In this case, I've just got some 2 spheres. I made this work perfectly. We can imagine this to be 2 cells. Maybe the cells have like a nucleus in here, and then they've got like a mitochondria and some other weird cellular things. Here's another cell down here, and it's got a few things in there. That's kind of a funny looking picture. But anyway, you know, you want a face on the bottom of that thing? Here, we'll do that later after I'm officially done doing what I'm doing here. But if these were cells, you could say, oh, look at there. 2 cells perfectly fit across. So then all we have to do is a simple division. Whatever you calculated the diameter of the field of view to be, divided by the number of objects, and you've got an estimation of how much one of those objects is, how big it is. So in this case, if we were under our last calculation, maybe 1,200 micrometers divided by 2, they're about 600 micrometers each. Okay? And just to complete the goofy picture, yeah, we'll put a smile here. What else do? You put it like a tongue sticking out like that or something like that? I don't know. Anyway. Yep. We're not worried about the rest of the space. We're worried about determining how wide or how the dimensions of the cell that's in there. So I'm only really worried about this distance across here. Now the picture's really getting goofy. Anyway, so we're worried about what that distance is there, okay? And if we know what the entire distance is, and we estimate that 2 of these fit across, then we know the size of that thing, right? We're really just getting an estimation. So when we look at cells like onion cells versus cheek cells, what we're really comparing are like plant cells versus animal cells, because we're animals, and we want to know whether there's a big size difference in those cells. So we're going to try to estimate the size of the cell, right? And we're really not getting official measurement numbers. We're just wanting to know about how big they are. Okay? All right. So let's just do a quick little example. And again, here I've got the same silly 2 objects. So let's say that we did our calculation of the field of view, and we found that field of view to be 450 micrometers. And we've got our 2 objects here. How many objects can fit across? 2. And therefore, the width of the object, well, how wide is the field of view? How many can fit across? It is that simple. Yep. 225 micrometers. Now again, this is an estimation. This really comes back again to our discussion on significant digits that we had, when we were doing optics. If we're saying that about 2 of them fit, let's say we're not dealing with a nice situation like this, but let's say our object, and maybe it's hard to draw on this one, let's say our object was maybe more like this, right? And what would you say? You'd say like 1, 2, 3, 3.5, about 3.5, right? So then to say something like 225 micrometers is almost too precise. You see what I mean? For this where there's just 2, yeah, I would say, you bet, 2 fit perfectly, 225 micrometers. But if I'm saying it's about 3.5, then I might not say 225, I might say 230, about. You see what I mean? And that's where we're really kind of estimating. If you were to write 3 digits, I wouldn't mark you wrong. I would say that's good calculation. But in reality, when you do an estimation, you really lose out on the exactness of your number because you're just kind of guessing. All right? Okay. So the calculation is pretty straightforward. We know how to get the field of view using our equation. All we have to do is get an image, and we need to estimate. Here's one more. We'll just leave it at that. Here, look at that. There's a good example there. Now, notice here I asked for the width of the object. I could do a second calculation for length, right? Width, I would say, is the smaller, because length implies longness, right? So I would say width is across the short length, the short distance, and then length is that long distance. So if we were saying the width of the object, I'd say that, the width, right? So how many would you think? What do you think? And it's truly an estimation. You're staring down the microscope and you're going, yeah, I don't know, 3.5, You think 4? 1, because this counts as 1, right? 2, maybe 3, 4. I like 4 as an estimation. I like that. That would be fine. Again, it's an estimation. Like, can you be wrong on this? I guess you could. If you said 1, I'd say no way, right? If you say 10, I would say, really? You're crazy. If you said 5, yeah, I would be stretching it. I would probably accept it, right? So the estimation can be wrong, but there's like 4.5. Oh, I'd buy 4.5. But we decided on 4, that's fine. So 450 micrometers divided by 4, and this is about 4. What do we got? Yep. 112.5. Wow, to 4 significant digits. Can we really say it, that it's exactly that? So what would we say? Might be acceptable? 110? 110? 112 I'd even take. 110. Really, it's approximately 110 micrometers? That's the wave. That's approximately. That's where the wavy equal sign stands for. Yep. Yeah, you don't have to write the normal and the wavy. You could just have one. You don't even need the wavy. I just wrote it that way because it really stands for approximately. You could do either or. Don't do both. That wouldn't look right. Okay? All right. Hey, let's do length. What do you think the length of this? What do you think the length of this one's going to be? 2? I think so. I would say 2. 1 and then a half and a half. I'd say 2. 450 micrometers divided by 2. And I'm using the equals, even though I might use a rounded number. Because what does that get us? 225, right? 230, 220, somewhere in there. Either or. 230 micrometers. That's the 2 digits. It's not bad. If you put 225, I'd still give you marks. 112.5, I'd like to go, really? I don't know. That might be a little too many digits. Are we okay with this 2-step process? Figure out the field of view, then estimate the number across. Okay. I do have one more practice problem that kind of flips it on its head. What if we know the fields of view? Can we figure out a magnification? The answer is yes. Is that not on the piece of paper? No? It was? Oh, it doesn't matter. If you got to write it, you got to write it. I was just curious. Oh, so you might have to write this one down. I might have added it in. I might have added it in. So you do have to write it even if you've got the paper. So if we could somehow figure out the diameters of the field of view, could we use it to find a magnification? I guess we could get an approximate magnification. Where would this be a case? Well, some cells have very defined sizes. So if we were under a certain power, we could actually count, right? We could count those cells. We could figure out how wide the field of view is. And then we could change to another power and count the cells again and figure out how wide that field of view is. So this is really just to change up the problem-solving process. So notice we're looking, well, what are we trying to find? Which variable am I trying to find in this problem out of our equation? Yep. High power magnification. Now, in the original equation that we had DH, over DL, right? And then we add ML, and then we add MH, which is what we want to find way down there on the bottom. Now, that's a real pain to solve for mathematically. But we can manipulate this equation. We have to keep in mind that it is an inverse relationship. So we can create the equation in whatever form we want, as long as we keep the inverse relationship. So if I'm looking for MH, I'm going to write it down first. What has to go underneath it? ML. Now, because it's an inverse relationship, which of the D's will go on the top? DL, because I had MH on the top on this side. And as long as we've got the inverse, it doesn't matter how we write it. It's going to be correct. So now we can solve it very much like we solved the other problems. Mathematically, we're going to multiply both sides, but it means we don't have to do any other tricky math. It saves us in some math work here. So MH is what we want to find. ML, the lower magnification, 50 times. DL, the low power field, 2,500 micrometers. DH, the high powered field, 250 micrometers. I'm going to multiply both sides by this 50 times 50, and then times 50 times, right? 50 times. We say that's the magnification. Can cancel out the 50s, and what do we get for a number? Yep, Allison? 500. So this particular microscope has a 500 times magnification under high. Okay? All right? So just to kind of guide you to this particular thing online here, well, you guys didn't do covalent bonding. You guys did. Today's work is determining the size of an object. Where are we? Calculating the field of view and width of objects worksheet. All right? That was the note we just did. So there's the worksheet. Actually, I already have it up. And it's really just a practice sheet. This is not to be marked. And I've already got the solutions in the course content under the biology unit in homework solutions. So when you finish it, you can check it. Okay? So it's just homework. It's just practice. Everybody understand that? Okay, at this point, I'm going to stop the recording, and we'll talk about what our experiment is going to be.